Welcome back to this session. In this lecture, we are going to see the basic definition of a complex number and a complex analytic function and how to construct the complex analytic function. The first definition is a complex variable z equal to x plus iy, where I is a complex number, and here x is called real part of the complex number z and y is called the imaginary part of the complex number z, and it is denoted as x equal to re of z and y equal to im of z. The second definition, the complex conjugate of the complex variable is z. Suppose z equal to x plus iy, then its complex conjugate is defined as z bar, that is equal to x minus iy, right? So geometrically what it says, if you have the complex number x plus iy here, that is x plus iy, then x minus iy is the mirror reflection of this axis. Okay, the x minus iy, it will be somewhere here. This is x minus iy. Okay, then the third definition is the modulus of the complex number. Suppose z equal to x plus iu is a given complex number, then what is the modulus? The modulus is defined as under root x square plus y square. Sometimes we used to call this the modulus of z, which is nothing but the length of the complex number. Length of complex number. Length of the complex number, right? Okay, then see, in the last few definitions, the complex variable is that written in terms of the Cartesian coordinates x and y. Sometimes we can write the complex number in terms of the polar coordinate, that is r comma theta. For this, we need x equal to r cos theta and y equal to r sin theta. Then z equal to x plus iy can be written as r cos theta plus ir into sin theta, and r is common, see, therefore take it outside. Then the remaining is r into cos theta plus I sin theta, which is equal to r into e power I theta. Now by using the Euler formula, what is Euler formula? E power I theta, which is equal to cos theta plus I sin theta. I sin theta, we can write z, which is equal to r into e power I theta. Okay, right. So next we see what is the definition of analytic function. Here f of z be a complex valued function, that is f is a function from set of complex numbers to set of complex numbers. So as like a complex variable z, this f of z is also having two components. One is a real part, another one is a complex part. That is, your u is the real part of the complex function f of z, and v is the imaginary part of the complex number. Now, the function f of z is analytic at the point z equal to z naught, means in a complex plane, if the function f of z is analytic at the point z equal to z naught, means there exists a neighborhood around this point at which the function which is differentiable at all the points which are sitting inside this neighborhood. So there is a neighborhood about the point z equal to z naught. In this neighborhood, the function which is differentiable at all the points. If it happens, then we can say the function which is analytic at the point. Analytic at the point, right? Right. Second definition, the function which is analytic on the region D. For example, we have the region like this. This is omega. If you want to say the function which is analytic on this region, means if I take any point in this region, then we can able to find out a neighborhood around this point. In this neighborhood, the function which is differentiable. For example, if I have taken another point here, and then we can able to find out a neighborhood around this point at which the function which is differentiable at all the points inside this neighborhood. For example, if we take another point here, then we can able to find out a neighborhood like this. Then inside the neighborhood, the function which is differentiable. That is the meaning of the function which is analytic on the region D. That means at every point inside the region, the function is analytic. That is the meaning. Right. Next note, the analytic function f of z is also called regular function or holomorphic function. Okay, these are all special names. regular, either we can also call regular function or holomorphic function. Right, here as I told, f of z which is equal to u plus iv, and here u is a function of x and y and b is a function of x and y. Right. Now what are the necessary and sufficient condition for the analytic function? Now let us state the necessary condition. Suppose if f of z which is equal to u plus iv is analytic, then u and v satisfy the Cauchy-Riemann equations, that is dou u by dou x equal to dou v by dou y, and dou u by dou x, dou u by dou y equal to minus dou v by dou x. That means the functions u and v satisfies these two relations, that is ux equal to vy and uy equal to minus vx. But this is not a sufficient condition. Okay, now what are the sufficient condition? The sufficient condition for the analytic function is if u and v satisfies CR equation, that is ux equal to vy and uy equal to minus vx, and all the partial derivatives are continuous, that is ux, uy, vx, vy all are continuous, then the function f of z is analytic. Then only the function is analytic. There are some function in which the Cauchy-Riemann equations are satisfied at some point, but the partial derivative may not exist or partial derivative may not be continuous at the point. See, therefore the sufficient conditions are also important. Right. So next one, the CR equation in polar form. As I told, the complex variable z can be written in terms of the polar coordinates r comma theta. See, therefore the complex function f of z can also be written in the form of polar coordinate, that is u of r comma theta and v of r comma theta. Then the corresponding Cauchy-Riemann equations in polar coordinates are dou u by dou r, which is equal to 1 by r into dou v by dou theta, and dou u by dou theta equal to minus r into dou v by dou r. These are the Cauchy-Riemann equations in polar form, and the Cauchy-Riemann equations in Cartesian coordinate system is ux equal to vy and uy equal to minus vx. What is ux? Ux means dou u by dou x, okay, and uy means dou u by dou y. Similarly for v. Right. Next we'll see some properties of analytic function. The first property is if f of z is equal to u plus iv is an analytic function, then u and v satisfies the Laplace equation. What is the Laplace equation? It is a second order partial differential equation, that is dou square u by dou x square plus dou square u by dou y square equal to 0. This is called a Laplace equation. Laplace equation. That means the functions u and v satisfies this second order partial differential equation. See what all given to us? The function f of z is analytic. See, therefore it satisfies the CR equation. The first equation is dou u by dou x equal to dou v by dou y, and second equation dou u by dou y equal to minus dou v by dou x. Okay. Then differentiate the first equation partially with respect to x and differentiate the equation partially with respect to y. Then we get dou square u by dou x square equal to dou square v by dou x into dou y. And then if we differentiate the second equation partially with respect to y, we will get dou square u by dou y square equal to minus dou square v by dou x into dou y. If you add these two, which gives 0, that is dou square u by dou x square plus dou square u by dou y square equal to 0. Okay, that is u satisfies the Laplace equation. Similarly, if you differentiate the first equation partially with respect to y and the second equation partially with respect to x, if you add it, then we will get dou square v by dou x square plus dou square v divided by dou y square equal to 0. See, therefore these two functions satisfies the Laplace equation. That's the first property. Then the second property is if f of z which is equal to u plus iv is an analytic function, then any constant multiple of f of z is also analytic. Okay, here c may be a real number or c may be a complex number. For whatever the constant c into f of z is analytic provided f of z is analytic. So what is given to us? f of z equal to u plus iv, and it is analytic. See, therefore it satisfies the CR equation, that is dou u by dou x equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. Now you multiply the function f of z by c, multiply the function f of z by c. See, therefore the left hand side is c into f of z, which is equal to cu plus I cv. Now let us redefine the real part and imaginary part of c into f of z as capital U. Capital U is cu, capital V is cv, and then the partial derivative of capital U is ux equal to c into ux, vx equal to c into small vx, and capital Uy equal to c into small uy, capital Vy equal to c into small vy. Okay, because c is a constant. C is a constant, right? These are the partial derivatives. If you compare the all partial derivatives, we can see that ux equal to vy and uy equal to minus vx. See, therefore capital U and capital V satisfies the CR equations. Hence our c into f of z is also analytic. Okay, and not only that, capital Ux, which is equal to c into ux, and capital Uy, which is equal to c into uy. Similarly, capital Vy, capital Vx. Since ux, uy, vy, vx all are continuous, therefore capital Ux, capital Uy, capital Vx, Vy all are continuous. Hence, it satisfies the both necessary and sufficient condition. Okay, right. See, therefore, c into f of z is also analytic. So while constructing the analytic function, we are going to use this result. Please keep it in mind. If f of z is analytic, then any constant multiple of f of z is also analytic. Right. Third property, if f of z is analytic and its modulus is constant, then the function itself constant. What it says, we have f of z and the modulus of f of z equal to some constant, means then the function f of z is a constant, right? So given that f of z is analytic, see, therefore u and v satisfies the CR equation. And what is the modulus of z? Modulus of z is under root x square plus y square, and f of z equal to u plus iv. See, therefore modulus f of z, that is equal to under root u square plus v square. Right. See, therefore modulus f of z is under root u square plus v square. Let me call this as c. See, therefore if we square on both sides, u square plus v square equal to c square. Let us call this as equation number 1. Now differentiate the equation 1 partially with respect to x. See, therefore you will get 2u ux plus 2 v vx equal to 0, and then we can cancel the common factor. So remaining u ux plus v vx equal to 0. But u and v satisfies the CR equation. See, therefore you can write u ux minus v into, instead of vx we can write it as minus ui. See, therefore u ux minus v into uy equal to 0. Let us call this as equation number 2. Now differentiate the equation 1 partially with respect to y, then you will get u uy plus v vy equal to 0. Again, by using the CR equations, we can write u uy plus v into ux equal to 0. Now we have two equations in terms of ux and ux into uy. Then we can group them. Then we can write it as the matrix equation ax equal to b form. Okay, ax equal to b form. Right. See, what is b here? Our b is 0. Okay. So here A is a square matrix which is of the form A11, A12, A21, A22, right? And X is a 2 cross 2, A is a 2 cross 2 matrix and X is a column vector. If the determinant of A equal to 0, then X equal to 0 is a solution, is the only solution. Okay. If determinant of A equal to 0, then x equal to 0 is the only solution. That's what the linear algebra says. So if you group the equations 2 and 3, you can write it as the matrix form like this, that is u minus v, v u, ux uy equal to 0 vector, and its determinant is u minus v, v u, that is equal to u square plus v square, but u square plus v square is c square, c is a non-zero constant. So therefore the determinant of this matrix is 0. Hence what it says, ux equal to 0 and uy equal to 0. Hence ux equal to 0 and uy equal to 0 by using this linear algebra results. So ux equal to 0. See, therefore if the partial derivative of u with respect to x equal to 0 means there is no x. Similarly, the partial derivative of u with respect to y equal to 0 means the function u does not have y. Okay, but u is a function of x and y. But the partial derivative equal to 0 means with respect to both the variables, means it must be constant. Right? For example, if u equal to x plus y, what will happen? Ux equal to 1, which is not equal to 0. And uy equal to 1, which is not equal to 0, right? But the condition says that ux equal to 0. Then what is the integration? If you integrate it, then you will get some c1, right? Some c1. Similarly, uy equal to 0, if you integrate this uy with respect to y, then you will get another constant c2. See, therefore, ux equal to 0 means there is no x, and uy equal to 0 means the function u does not have y. That is, u must be a constant. This, by using the similar argument, we can also prove that v is also constant, right? If u is constant and v is constant, then the function f of z, which is equal to u plus iv, equal to some constant. That's what the statement says. If f of z, which is equal to u plus iv, is an analytic function with the constant modulus, then the function is constant. Okay, right. So next, we'll see some problems whether the given function is analytic or not, or how to check the analyticity of the given function. The first example is test the function f of z equal to z square is analytic or not, and then find its analytic region. Analytic region means we have to find out the region in which the function which is analytic, right? What is f of z? F of z equal to z square, but z is x plus iy. See, therefore x plus iy the whole square, by using the formula a plus b whole square, which is equal to a square plus 2ab plus b square. Use this formula, then we'll get x square plus I y the whole square plus 2ixy. But I square is -1. Okay, I square is -1. See, therefore x plus iy the whole square, which is equal to x square minus y square plus 2ixy. Okay, now you group the terms, real part and imaginary part. See, luckily we have this real part, and then the imaginary part is simply 2xy. So let us call your u of x comma y is x square minus y square, and v of x comma y is 2xy. Okay, right. Now compute all the 4 partial derivatives, ux, uy, vx, vy. What is ux? U equal to x square minus y square. See, therefore, if you differentiate this partially with respect to x, that gives simply 2x. And then uy, differentiate this partially with respect to y. See, therefore, minus 2y. And v is 2xy. See, therefore, vx equal to partial derivative of v with respect to x, which gives 2y. And partial derivative of v with respect to y, which gives 2x, right? Now, if you compare this, ux equal to 2x, and vy is also 2x. Therefore, ux equal to, this gives ux equal to vy, and then uy equal to minus 2y, that is equal to minus vx. See, therefore uy equal to minus vx. That means the function u and v satisfies the CR equation. Not only that, what is ux? It is a polynomial, first degree polynomial. And uy, it is also polynomial. Vx, it is also polynomial. Vy, it is also polynomial. As we know that every polynomial is a continuous function. Hence, all the 4 partial derivatives are continuous. Hence, the function f of z, which is equal to z square, is analytic. Where it is analytic? We didn't specify any point, right? We didn't specify any point. See, therefore, the function which is analytic at all the points in the complex plane. So that's what given here. The CR equation which is satisfied at all the points in the complex plane. See, therefore, the function which is analytic in the entire complex plane. Hence, which is analytic in the entire complex plane. Right. So next example, f of z equal to z bar. What is z bar? Complex conjugate. Complex conjugate. Right. So given that f of z equal to z bar, and we know what is the complex conjugate, see, therefore x minus iy. Okay, that is x minus iy here. So from this, you extract your real part, that is u of x comma y equal to x, and the v of x comma y is minus y. Then the partial derivative dou u by dou x is 1 and dou u by dou y is 0, and dou v by dou x is 0 and dou v by dou y is minus 1, right? If you see that ux equal to 1, but this is equal to minus vy. See, therefore, what it says, ux which is not equal to vy. So the first equation, first CR equation is not satisfied, whereas the second equation is satisfied. So if at least one of the CR equations are not satisfied, then the function is not analytic. The CR equations are not satisfied, so therefore the function is not analytic. And another note, if the function f of z involves z bar, then the function f of z is not analytic. Okay, right. Okay, now let us see the next example. Test whether the function f of z equal to sin z is analytic or not, and then find the analytic region. Right. Given that f of z equal to sin z, okay, where z is x plus iy. Okay, f of z is sin z, but z is x plus iy. See, therefore sin of x plus iy. And we have to use the trigonometric identity. What is sin of a plus b? Sin of a plus b is sin a cos b plus cos a sin b. Okay. And another identity, cos ix, which is equal to cos hx. I is a complex number. Cos hx means it is a hyperbolic function. And similarly, sin ix, which is equal to I sin hx. Okay, these are the identities which we are going to use. So by using the first identity, sin of a plus b equal to sin a cos b plus cos a sin b, we are writing sin x cos iy plus cos x into sin iy. And by using the second and third identity, we are writing sin x cos hy plus I cos x sin hy. Right. Now from this, what is your u of x comma y? U of x comma y is sin x into cos hy, and v of x comma y is cos x into sin hy. Now compute the partial derivatives. Ux, what is the derivative of sin x? d by dx of sin x is cos x. Okay, and d by dx of cos x is equal to minus sin x, and d by dx of cos hx, which is equal to sin hx, and d by dx of sin hx equal to cos hx. Okay, these are the formulas. So by using these formulas, let us compute the four partial derivatives. Ux equal to, so what is this here? Ux is cos x into cos y. Why? Because u is sin x into cos hy. If we differentiate this partially with respect to x, the derivative of sin x gives cos x. See, therefore ux equal to cos x into cos hy, and uy is sin x into sin hy. Vx is minus sin x into sin hy, and Vy is cos x into cos hy, right? So now Ux is cos x into cos hy, which is same as your Vy, and Uy, which is sin x into sin hy, which is nothing but your minus Vx. See, therefore Ux equal to Vy and Uy equal to minus Vx, right? See, therefore the CR equations are satisfied. So this function satisfies the CR equation, and all the partial derivatives ux, uy, vx, vy all are continuous. Therefore the function f of z is analytic. Okay, so which is analytic at all the points in the complex plane. See, therefore the function which is analytic in the entire complex plane, right? See, next we'll see the another beautiful function. This is called harmonic function. Already we have seen such a function, but I didn't named it. First observation, from the property 1, we see that the real part and the imaginary part of the analytic function f of z satisfies the Laplace equation. Okay, that is, the solution of the Laplace equation is called harmonic function. Okay, the solution of the Laplace equation is called harmonic function, or sometimes we used to say this is wave function, either harmonic function or wave function. Okay, right. Then second observation, the imaginary part v of x comma y is a complex conjugate of y. Similarly v is a complex conjugate of y, and u is a complex conjugate of v. Okay, now the theory of harmonic function is called the potential theory. There is a theory which is potential theory, which is dealing with harmonic functions, right? Now property number 4, if f of z, which is equal to u plus iv, is an analytic function, then the level curves, why we are saying this as a level curve means u is a function of x comma y, u is a function of x comma y. If it is equal to some constant means, then we can write y equal to some function g of x comma c, or x which is equal to some h of y comma c. See, therefore either way we can get one curve. See, that's why we call this as level curve. So if f of z is analytic, then the level curves u of x comma y equal to c1 and v of x comma y equal to c2 form an orthogonal system. That means they meet perpendicularly. Right? So let us see the proof. Given that f of z equal to u plus iv, and u and v are satisfies the CR equation, that is ux equal to vy and uy equal to minus vx, u equal to c1, where c1 and c2 are constants, then what is the total derivative of u? The total derivative of u is, if f is a function of x comma y, then the total derivative is dou f by dou x into dx plus dou f by dou y into dy. This is called the total derivative. Now by using this definition, the total derivative of u is dou u by dou x into dx and dou u by dou y into dy, but the right hand side is 0, see therefore right hand side is constant, see therefore derivative of constant is 0. Okay, see therefore the slope of this curve is m1, which is equal to dy by dx, which is equal to minus ux upon uy. Similarly, if v equal to c2, then the total derivative is dou v by dou x into dx plus dou v by dou y into dy equal to 0, and its slope is dy by dx equal to minus vx upon vy. If you multiply the slopes m1 and m2, we'll get ux divided by uy and vx divided by uy. By using the CR equation, we are arriving that the product of two slopes equal to 1. In the lower class, we have seen that if the product of two slopes are negative, then the curves are perpendicular. Then the curves are perpendicular at the point, right? That's what this says. So the geometry says that if m1, m2 equal to minus 1, say therefore these two curves meet orthogonally. That is orthogonal system. Right. Now useful observation or note, in fluid flow problems, the level curve u of x comma y is called equipotential line, and the level curve v of x comma y equal to c2 is called streamline. Right. Now let us see how to construct the analytic function by using the well-known Miline-Thomson method. There are two methods under Miline-Thomson method, or two cases. If the real part of the analytic function is given, then how to construct the analytic function? There are 4 steps involved in this. Similarly, if the imaginary part of the analytic function f of z is given, then how to construct the analytic function f of z? Let us redefine the first one as a first method, or method 1. If the real part u of the analytic function f of z is given, then your f dash of z is the first derivative. F dash of z is ux plus I into Vx, but u is given. See therefore, by using the CR equations, you rewrite V in terms of u. Okay. See therefore, Vx equal to minus Uy by CR equation. See therefore, what is your f dash of z? F dash of z ux minus I into uy. Right. Now the only function ux is given. See therefore, write f dash in terms of ux and uy. So the step number 1, you compute dou u by dou x and dou u by dou y. Then step number 2, replace in ux in uy, wherever x is there, you just replace x by z and then y by 0. See therefore, ux is going to be the function of z. Similarly, ux is going to be a function of z and uy is also a function of z. That is a step number 2. Then step number 3, plug the function ux and uy, that is f dash of z equal to ux of z comma 0 minus I into uy of z comma 0. But we want the analytic function f of z. But f dash of z is given. See therefore, if you integrate it, that is integral f dash of z into dz. If you integrate this with respect to z, we will get back the function f of z. See that is your step number 4. So integrate f dash of z with respect to z, then you will have integral ux of z comma 0 into dz minus I into integral uy of z comma 0 dz plus integrating constant c. So if you integrate this, we will get the function f of z. Right. Method 2. If the imaginary part v of x comma y of the analytic function f of z is given, then what is the first derivative? F dash of z equal to ux plus I vx. But only v is known. See therefore, you rewrite ux in terms of v. But by using the CR equation, vy equal to ux. See therefore, replace ux by vy. Right. Then you find out what is your vx and vy. Replace x equal to z, y equal to 0 in vx and vy. That is a step number 2. Then you redefine your f dash of z in terms of vx of z comma 0 and vy of z comma 0. Then you will get f dash of z equal to vy of z comma 0 plus I into vx of z comma 0. That is step number 3. Then you integrate, because f dash is known. If you integrate this f dash of z, then we will get f of z. Okay, see, therefore f of z, that is equal to integral f dash of z into dz. So integral f dash of z equal to integral vy of z comma 0 into dz plus I into integral vx of z comma 0 dz plus integrating constant c. That gives the required analytic function. Next we'll see some example problems. Example, prove that u of x comma y, which is equal to e power x into cos y minus sin y, is a harmonic function, and hence find the analytic function f of z. Okay, so that means the underlying assumption is u is the real part of the f of z. Okay, and we have to calculate, or we have to find out what is v. Right, if you know what is u and v, then we can add it up. So which one is given? The real part of the analytic function is given. See, therefore we have to apply the method 1, Miline-Thomson method 1. So what all given to us? U, which is equal to e power x into cos y minus sin y. See, therefore if you compute the partial derivatives dou u by dou x, which gives e power x into cos y minus sin y, and uxx, which is equal to e power x into cos y minus sin y, because with respect to x, we are treating cos y minus sin y is constant. And then what is the derivative of e power x? D by dx of e power x is e power x. Similarly, d square by dx square of e power x is again e power x. Right. Then what is uy? Uy is partial derivative of u with respect to y. So e power x into derivative of cos x is cos y is minus sin y, and the derivative of sin y is cos y, so therefore we have minus cos y here, and uyy, that means you have to differentiate this again with respect to y, so therefore e power x into cos y plus sin y. Then you add uxx and uyy, that is e power x into cos y minus sin y plus e power x into minus cos y plus sin y, that gives 0. So what it says? It says that u satisfies the Laplace equation, that is, it is a harmonic function. Right. Now we have to calculate the analytic function f of z. So what is a Miline-Thomson method? One says that if the real part u is given, then compute ux, uy, and then replace x equal to z and y equal to 0 wherever x is there and wherever y is there. Okay. Then you redefine your f dash of z equal to, what is the formula? You redefine f dash of z equal to ux of z comma 0 minus I into uy of z comma 0, then integrate it. Okay. So already we have calculated all the 4 partial derivatives. So ux of x comma y equal to e power x into cos y minus sin y, and uy of x comma y is e power x into minus sin y minus cos y. See, therefore ux of z comma 0, wherever x is there, you just replace x by z. See, therefore e power z, and cos 0 is 1 minus sin 0. See, therefore this term, that gives e power z, and uy of z comma 0 is e power z minus 0 minus 1. See, therefore minus e power z. And then your formula is, what is the formula? F dash of z, which is equal to ux of z comma 0 minus I into uy of z comma 0. Right. Already we have calculated what is ux and uy. You plug these two expressions in this formula. So f dash of z is e power z plus I into e power z, that is 1 plus I into e power z. And then integrate this, that gives f of z. See, therefore integral 1 plus I into e power z dz plus integrating constant c, and then we are getting 1 plus I into e power z plus the constant c. Okay, this is a required. It is f of z, which is equal to 1 plus I into e power z plus constant. This is a required analytic function corresponding to this real part. Okay. So next we move to the next problem. If v which is equal to 3x square y minus y cube, then find the analytic function f of z. So what is given? The imaginary part of the analytic function is given, right? So v which is equal to 3x square y minus y cube. So now compute the partial derivatives. Vx equal to the partial derivative of this with respect to x, therefore 6xy. So 6xy, only 6xy here. Okay, then Vxx is 6y, right? And then Vy, what is Vy? Vy is 3x square minus 3y square, and Vyy is minus y. Okay, see therefore if you add Vxx and Vyy, that gives 6y minus y equal to 0, right? That is, V satisfies the Laplace equation, therefore V is a harmonic function, right? So the real imaginary part of the analytic function is given, so therefore we have to apply the method 2. What is the method 2? There are 4 steps. First step is calculate Vx, Vy, and then you calculate Vx, Vy, and then substitute x equal to z, y equal to 0. Then you put it in the formula f dash of z is, what is f dash of z? Vy of z comma 0 plus I into Vx of z comma 0. Okay. Then you integrate, that gives the required analytic function. So already we have calculated what is Vx. Vx is 6xy, and Vy, this is 3x square minus 3y square. Then substitute x equal to z and y equal to 0. See therefore you will get Vx of z comma 0 is 0 and Vy of z comma 0 is 3z square. And then your formula f dash of z is Vy of z comma 0 plus I into Vx of z comma 0. If you plug these two values, then you will get 3z square plus I into 0. Okay, see therefore 3z square. Now integrate this. If you integrate this, integral 3z square dz plus integrating constant c, that gives z cube plus c. Okay, that is a required analytic function. So next we move to the next problem. Find the analytic function f of z which is equal to u plus iv. But given that the combination of u and v, that is 2u minus 3v which is equal to e power x cos y minus sin y. So in the last two examples, either the real part is given or the imaginary part is given. But in this problem, the combination of both the real and imaginary is given. See therefore, we have to multiply the unknown f of z by suitable constant in order to get 2u minus 3v, right? So look at this, f of z equal to u plus iv, but I wanted 2u, so therefore multiply the equation 1 by 2, that gives 2f of z equal to 2u plus I 2v. The second component is I want minus 3v. We know that I square equal to minus 1. See therefore if you multiply the first equation by 3i, then you will get 3i f of z equal to 3iu minus 3v. If you add these two equations, then you will get f of z into 2 plus 3i equal to 2u minus 3v plus I into 2v plus 3u. Okay. Now let us define capital F of z is small f of z into 2 plus 3i and capital U which is equal to 2u minus 3v and capital V is 2v plus 3v. Then what is given? So from this expression, capital U is given, that is the real part of capital F of z is given. See therefore apply the Miline-Thomson first method, right? So after all, we we have to multiply the given function f of z by a suitable constant in order to make the given expression as either the real part of the new function capital F of z or the imaginary part of capital F of z. That's all. Then apply the corresponding Miline-Thomson method. So luckily, see, if you multiply by f of z by 2 and then again by 3i, if you add it up, which gives capital F of z and then which gives a capital U. See, therefore we apply the Miline-Thomson first method, right? So capital Ux of x comma y is e power x into cos y minus sin y, and the capital Uy of x comma y is e power x into minus sin y minus cos y, and then put x equal to z and y equal to 0. See, therefore you will get e power z and then here minus e power z. Then by first method, capital F dash of z is, what is this, ux of z comma 0 minus I into uy of z comma 0, that gives 1 plus I into e power z. And then integrate this capital F of z, that gives integral 1 plus I into e power z dz plus c. See, therefore the integration gives 1 plus I e power z plus c. So that is capital F of z is 1 plus I into e power z plus c, but we are looking for what is small f of z. But what is the relation between capital F of z and small f of z? Capital F of z equal to small f of z into 2 plus 3i. See, therefore your small f of z is 1 plus I divided by 2 plus 3i into e power z plus c divided by 2 plus 3i. That is the required analytic function. Okay, this is a way to calculate the analytic function. Sometimes they will give the expression like this. What is 5u plus 3v? So f of z, which is equal to u plus iv, I want 5u, so therefore you multiply this function f of z by 5, so therefore 5 f of z, that gives 5u plus I into 5v. And then I want 3v's, therefore multiply this function by minus 3i f of z, that gives minus 3i u plus 3 into I square minus I square, but minus I square is 1, so therefore v. If you add these two, you will get 5u plus 3v plus I into 5v minus 3u. Okay, so we got this expression 5u plus 3v, right? We have to multiply the suitable constants. We have to identify the suitable constant and then multiply in order to get the expressions like this, right? Okay, thank you.